Hello everyone. Welcome to our webinar. We're so glad that you could join us. My name is Debbie and I'm here just to give you a couple of quick administrative notes before we get started. First of all, you are all in listen only mode, which I'm sure you're familiar with. That means that you can hear us, but we cannot hear you. If you have questions as you listen, be sure to jot them down, and at the end of the webinar we'll give you some email addresses and ways to send those questions in and get some answers. Our hosts today are Javier Solá and John Iriberri. They are business partners who are cycling insiders and problem solvers. Javier is the CEO of trainingforall.com and John is the CEO of custom4.us. And John unfortunately had a family emergency come up last minute, so he is not with us yet, but he may be able to join us a little bit later. But for now, Javier is our host. And I believe we are ready to get started. So Javier, I'm going to switch the screen to you and you can take it away.
Thanks, Debbie.
You're welcome.
Okay, thanks. Everyone can see the screen, I think, no?
Yes, I can see it.
Yes, okay. First of all, my apologies because my partner John has a problem in the last hour. So he will try to join during the webinar if it's possible for him. So I will try my best in this webinar. So the webinar today is about pedaling effectiveness and how we WKO4 we can use it, and we can give some feedback to our cyclist about his pedaling technique and how to increase the mechanical efficiency. First of all, we have to know that when a cyclist applying a force over the pedals, this force is formed by two different forces. The first one is the tangential force, which is this one, and this force is in the same direction of the movement, so it's the force that is responsible of the movement of the bike. And the other force is the radial force. This force is not in the direction of the movement, so doesn't contribute to the movement of the bicycle. There are another two forces that are very interesting, that are the muscular and the inertial force, and they are a little stuff of research of that force because they are very, very interesting. Because as you can see in this analysis, in this is my image, part of the total force that you apply to the pedals is muscular or inertial. For example, the type of materials, the wheels that you use, for example, contributes to the inertial of the total force. So there is a need to investigate or research about this force, because nowadays tangential and radial are the more clear of them. So with WKO4 we can see more clearly tangential and radial, and with some example we're going to see later. Okay. We are going to see now some definitions that could be important to understand the webinar. The first one is mechanical efficiency, and we can define it how carrying out a movement with less work from the mechanical point of view. So we try to make the movement with the less work possible. The other definition is gross efficiency, is the percentage ratio of external work achieved compared to total energy expenditure. This is a percentage of effort, or we can see that is how much external work we need in comparison of the total energy that we use for doing the movement. The other one is metabolic efficiency, is the level of caloric waste of the body. You know that the only way to measure that is with a mask in the laboratory. And the last one is the delta efficiency. It measures the difference of mechanical efficiency changing workloads. We compare the workout output between different workouts and different expenditure of energy in each load. So with these four definitions, we can go on with the webinar and understand better all the things that we are going to explain. About the muscular and non-muscular forces that we have explained before, that there are some part of the force are muscular and inertial. Couch in 1983, he's made some research, and you can imagine that in that day he hasn't enough technology as we have today, and he has started to discover that you can see here in the image that in top the center, the cyclist used to brake the pedals and doesn't contribute to the movement. So he started to suspect that there were a component of non-muscular force in that part of the pedaling cycle. So now we are going to explain two classic metrics of pedalings that everyone who has a dual power meter can see in the analysis of the workout, and these two metrics are the torque effectiveness and the smoothness. I think that everyone has read about this, but I'm going to explain just in case. The torque effectiveness is how much power are you deliver to the pedal, pushing it forward, and it's calculated with P positive. And this part of the pedaling is when we are doing the power phase, so from to top the center to the bottom the center. This is positive energy or power, and with the negative power, you make this one P plus P negative, and the percentage of that represent how much power is useful for us when pedaling. Cyclists who brake the pedals, for example, tend to have more negative force here and less positive force or power here. The other one is smoothness, and this one is playing how smoothly power is delivered to the pedal through the revolution. It's calculated with the division about power average and P max, and explain more or less how punchy or how smooth you pedals. For example, if you have a value of 100%, that says that you are delivering constantly the power. That is impossible, and then normally the percentage of this is between 10%, 40%, and in this one the normal values are between 60% and 90%. These metrics in WKO4 you can see in that chart in pedaling effectiveness and pedaling smoothness, and we track over the season how the pedaling effectiveness, torque effectiveness, is changing over the season. For example, you can see here that cyclists in both legs, the power effectiveness is over 80%, and you can see again the smoothness in both legs. Normally, there is a relationship between them. For example, you see when pedaling effectiveness starts to decrease along the season, it's normal that at the same time the smoothness decrease because both of them used to have a relationship between. Now we have said that we have the classic metrics, but now thanks to WKO4 we have metrics to make a deeper analysis. These metrics are gross power release, the first one you have here, and the other one is gross power absorbed. We can make a relationship between gross power release with the tangential force, because it's the power that you are releasing on each pedal stroke to propel the bicycle forward. So it's very interesting. It has a big relationship between the tangential force and the gross power release, and the other one is gross power absorbed. this one has the relationship with the radial force, the power that is being produced, but it's not going to moving the bicycle forward that is being absorbed, the opposite vector of GPR. So this power is useless, and this one is useful. And the relationship between these two forces is the Kurtotic Index, how punchy or smooth you are pedaling a stroke, and the higher the number, the more punchy your stroke. So the Kurtotic Index could give us an idea about what is the level of the pedal technique of the cyclist. And normally, a good value of Kurtotic Index is 4 more or less, but the lower is this value, the smoothness you pedal. So we have studied some different cyclists, and later we're going to see more or less the normal value for pro cyclists and the normal values for amateur cyclists. When we are going to make a study about how the professional riders pedaling techniques, the most of them we have seen that they have lower values of GPA. You can see here that they have a lot of gross power release, in this case 139 and 128, but the GPA is so low, 13 and 16. But if we compare with an amateur rider, we can see this graph how the GPA is higher than the pros. Obviously, there are pros who has a worse pedaling technique than the others, and other pros have better pedaling techniques. But in general, the most of the pros have good values of GPR and low values of GPA. So the Kurtotic Index in pro riders, the Kurtotic Index in pro riders are much better than the amateur rider. Here, this is the first one image. You have the Kurtotic Index of a pro rider. You can see his value is under 3.5, and the amateur rider has a big value compared with the pros. He's close to 4. You can see how when the seasons go on, this value is going lower, because we are going to see now with different evidence how the mechanical efficiency is going to increase with the intensity of the trainings of the competition. That's the main difference between the pro and the amateurs, the intensity of the trainings and the competition. So the mechanical efficiency trend is to go lower, go higher, and obviously the Kurtotic Index goes down along the season. This is one of the best studios about, or research about Thomas Cord. He's one of the best researchers in pedaling technique, and he explains that when they have a group of cyclists and they were told to alter their pedaling technique. You can see that when the cyclists were told to pedal with circling or pulling, the pedals, the mechanical efficiency increase. You can see here how the peak is much more lower than the pushing pedaling, but in the negative part, this was a less value. But at the same time, it worsens the metabolic efficiency. So the conclusion of the study is that the improvement of mechanical efficiency altering the technique normally worsens the metabolic efficiency. So it's one of the conclusions of the study is that pushing pedaling is less mechanical efficiency, but increase the metabolic efficiency. Another study of Laerdal explained that there is no relationship between mechanical efficiency and gross efficiency, and there were no relationship with the saddle setback. There were no difference between putting the saddle at the front or at the back, and no relationship with the percentage of the climb. the only factor that affect the metabolic efficiency was the cadence. It's important to tell your cyclist to self-select cadence. When we have to tell him to use a different cadence, normally the metabolic efficiency worsens. That's this study. This is another study about Busco in 2005, and in that study he makes allowed of 300 watts to 15 watts. You can see here the allows, okay? And he explains that the more intensity, the more mechanical efficiency. So that means that mechanical efficiency improves with intensity. Later we are going to see different examples with WKO4 how this occurs, okay? Here in the same study, he compared different cadence, 40 RPM, 16 RPM, 18 RPM, and 100 RPM. Both are aggregate when we separate in a sense of the self-selected one. So, like the other study or research, if we told the cyclist to use a cadence that they are not used to do, the metabolic efficiency decrease. There is another interesting study by Cannon in 2007 that explained that ankling, this is when the heel drops, when we are at the power pass over the 3 o'clock in the pedaling circle, makes that this situation increase the AMG of hamstrings and gastrocnemius, and obviously increase the metabolic increase. In this case, we can study with pedaling metrics of WKO. For example, you can see here. In this case, you can see how the heel drops this point of the pedaling phase, power pass, and what happens when that occurs. You can see how the GPA of the right leg increase. At this time, the cyclist think that he's making more power because he has this sensation, and you can see at the same time that the GPR is increasing, but at the same time that makes that the GPA increase. Why increase? Because he is braking the pedals. Why is braking? Because the direction of the force is not tangential, it's radial at this time. In Pioneer, for example, or Pioneer cyclometer analysis, you can see how the right one, when he's doing the power pass, the direction of the vector is not in the same direction of the movement like the left one, for example. So you can check here how ankling increase the metabolic cost, as we have seen in the study of Cannon, but at the same time, the mechanical efficiency decrease at the same time. You can see how GPA increased so much in compare with the left one, the leg which is not ankling.
Hi, Javier. I mean, if you want, I can help you if needed.
Thanks, John. Welcome, and I hope it's okay.
Yeah, sorry everybody about the delay. I will try to maintain myself connected.
Okay. So you can explain if you want anything, but I was explaining now. Yes.
Yeah, this is one of the main important screenshots of the presentation, because at the end, it's one study that justifies that the high intensity interval training is one of the most useful ways of increasing the metabolic efficiency. There are not so many things as we are going to be during the presentation that they can increase in an effective way the mechanical efficiency and the metabolic efficiency at the same time. So the HIIT training is one of them, and it's very clear on this study because if the intensity of the training is not high enough, the mechanical efficiency and the metabolic efficiency is not going to grow up. So this is maybe one of the most important conclusions of our webinar.
Okay. Now this study about Terrell in 2002 explained that with feedback on mechanical efficiency, we can increase it, but at the same time the metabolic efficiency is not altered. But the subject is fatigued before. Why probably the situation? Because the cyclists have to do a big effort, a mental effort, to doing the pedaling technique proper, like he's told, and that make that the fatigue occurs soon. Another study explained if the clip position have any repercussion in metabolic efficiency. This study explained that putting the clip forward or backward or in the metatarsal zone doesn't affect the mechanical efficiency and metabolic efficiency too. Anything to say about this, John? About the clip position?
No, just one of the things that maybe makes the biggest mistakes that can be made during the analysis of the mechanical efficiency. Several times we can arrive to some misunderstood conclusions about this. So if you change the position of the clit, for example, you are going to feel different things about the mechanical propulsion, or probably they are going to change several numbers in the mechanical efficiency. But from the point of view of metabolic efficiency, nothing is going to change. So probably this is one of the most confusing things, because there is people that change the clits depending on the supposed mechanical efficiency change affecting the metabolic efficiency. But this is not true. So this is also a very important conclusion of the webinar.
Another topic is the importance of the core in the position of the bike. Everybody thinks that it's very important. I think too. But the different studies, like Wakeman, speak that doesn't improve the gross metabolic efficiencies, but the perception of the force of the soldier improves. It seems to have less fatigue by perception because they have a good training of the core. About torque and gross metabolic efficiency, this study of Cameron explained how the median torque of the cyclist, and now when he goes, the median torque is the more efficiency, and when he goes up or down, that his median efficiency, this one is altered and decreased at the most of the time. That has a big relationship with the cadence that the cyclist use. Because when the cyclist is in obla or in anaerobic threshold, when the cadence increase, this gross efficiency decrease because he's using a cadence that is not used for to use. We have seen in other studies. Here we have metabolic efficiency meta-analysis by Bill 2013, and he explained that metabolic efficiency is decreased when we want to increase that mechanical efficiency. This metabolic efficiency decrease too when the field decrease. This one means when the cyclist adopt a very aggressive position and the sudden setback do not affect. It's not related to the experience of the cycling. This means the level of cycling of the years of practice or the fatigue. That are the conclusions of being in 2013 about the different research made till the date 2003. This study now is going to explain us, it's very interesting, about Pachitsky in 1980 about the use of the hip flexors and knee extensors. John, are you in? Yes.
Yeah, I am. No, just maybe it's necessary to comment on this screen that this is one of the first studies made to try to compare the different way of pedaling, and in this study Takaishi demonstrated that the one of the most important things from the point of view of mechanical efficiency is to try to pull up on the pedals, to try to not stop them and don't create an GPA phenomenon to stop the pedaling and avoid to increase the GP error in a not very useful situation. So the way of increasing the mechanical efficiency of this way is to try to pull up. This is one of the important conclusions of this study, but obviously it's going to be different from the point of view of the studies that are presented on this webinar. So they are very different conclusions at the end of the day.
This is one of the most important slides of this webinar. It's made by Jobson, and he's explained in his study that the most important in the pedaling technique is to have a big peak in the power phase, and you can see here, and a lower valley as possible. We call peaks and valleys. The lower valley and the high peak improve the mechanical metabolic efficiency. As you can see here, in this situation, to 22%, which is a big value. And in this graph in the right, you can see when the average minimum torque is the less possible, in this case, for example, 2 or 4, the gross efficiency increased. I think John have the data about this study, I think. They were with professional riders, all of them, in British cycling.
Yeah, they were at this moment on British cycling, and probably some of them they are actually on the Sky professional team. So it's very important from the point of view of demonstrating that the way of pedaling from the point of view of the management of the torque during the pedaling is very important and very closely related with the metabolic efficiency. So this is one maybe of the biggest conclusion of this study, and it's going to be key at the end of the conclusion of this webinar.
This study of Coyle in 91 is one of the most classic studies, explain that the mechanical torque is greater in elite cyclists or in pro cyclists. In the phase when they are lowering the pedals. You can see peak is here, and this peak is more higher than the other one. This study has a big relationship with this one of Juan Garcia in 2009, and explain more or less the same, that the professional cyclist has a better torque in the power class than the other one. The conclusion explained that it could be maybe from his experience of their expertise in pedaling. This one is another study of Bini, 2013, and explain how the torque decreased when the cyclist decreases the cadence. It doesn't use self-cadence, and when it decreases the tilt. That's another study we have seen before. The lower the cyclist goes, more aggressive position, the torque decreases, and increase with more intensity and more resistance, and with feedback. And there are no change when the saddle position is has any modification, or with fatigue or years practice. We, for example, have a study with WIVA, is an accelerometer. We have studied how the torque change in different situations, and they have similar conclusions that been in 2003. Anything to say, John?
No, I think that the study at the end of the webinar of Takahashi explained it better this phenomenon from the point of view of the change of the speed of the pedaling and the change in the mechanical efficiency. So we can follow on.
Okay. Another study of Bertucci in 2008 explained more or less the same, that the professional cyclists have the peaks are equal more or less, but they are prolonged in the time, on the time. So they have better peaks than the no-pro cyclist. About asymmetry, like we have seen in the other webinar about asymmetric cycling, there were no relationships between leg dominance and intensity, and retraining is good, a good strategy to correct this asymmetric index. With WKO4, you have a chart when you can monitorize the power balance of the cyclist along the system. And for example, this is one of our cyclists who have a power balance in some times of some parts of the cycle, between of 55, 45, 50, 53, 47, and he was told to come to the studio, and we were telling him how to retrain the pedaling technique, because he hasn't got any other problem, only a bad pedaling technique. When he was told to make one thoroughly, the power balance starts this at the Bini research suggests. This is another study of Bini we have seen in the other webinar, and there was no relationship between performance and asymmetry. The more asymmetry you have, you don't have to affect the performance, but obviously there is tension at the comfort when you have asymmetric positions, better than when you are asymmetric, more or less. Yeah?
Yeah, this is a quite famous study, and as we explained it in the seminar, actually it's not clear the relationship between the asymmetry and the performance. So we cannot conclude being very symmetric is, from the point of view of mechanical efficiency or metabolic efficiency, better than not being symmetric. Maybe it's necessary more research on this area.
This study of scouts in 91 is very interesting because have a strong relationship with other studies, and explain how with high intensity improves mechanical efficiency at equal currents. That explain other studies or even data we have in WKO4, or explain why pro riders have better mechanical efficiency than amateur riders. The reason could be the intensity. They train harder, they train more. That is the reason that they push harder than the amateurs. Here we have an example of WKO4 of amateur riders. He's doing a workout with some intervals, and you can see here below that when the average data of GPA in the workout is so high, 42 and 39, but when this cyclist was told to make the intervals, you can see the two intervals, all of them were at the intensity of FTP. Now, you can see how in those intervals, the GPA decreased from 40 to 30. That have a relationship with how the thing we have explained. So the more intensity we have to make, the lower GPA or lower radial force in our pedaling technique. So it's important to work the intensity or send workouts with intensity to improve the mechanical efficiency. Something to add, John?
No, I think that it's very well explained by yourself, so you can follow on.
Okay. There is another example in which the cyclists have to do a harder workout. In this case, they are a workout at VO2 max, and you can see how the more intensity, the lower GPA. So that's the other workout. In this one, which is more intensity, the lower GPA, so that improves the mechanical. Here there is a study that is going on now to explain to you, John, the the difference between sitting and standing. And for example, 2 days before, Contador said that he produced much more power in a sitting position than standing, something that the research doesn't say the same.
Yeah, from the point of view of the mechanical efficiency versus the standing and sitting, Boyor demonstrated that there increases when the mechanical efficiency is doing seated in comparison with stepped. Anyway, he comments that sometimes happens that very adapted subjects can do exactly the same. So it's not a very clear and universal conclusion that can be used for everybody. The general conclusion that is different, the mechanical efficiency, and maybe the point of this slide is that probably you could need to analyze each subject individually to know exactly if it is better or worse to pedal in seated or stand up.
Another topic that is very common, and most of the cyclists have some doubts about that, if the change to the crank of the front leg affect the mechanical efficiency. This study about Roca in 2014 explained that the change of the crank doesn't change the metabolic efficiency, but increase the torque in different parts of the super. But the average torque is the same, only change the tips of them. At the same time, this irregular distribution of the torque decrease 1 and 2% the mechanical efficiency. So in normal, changing the crank length doesn't affect the metabolic efficiency. In some cases, decrease. Another study about talking about the use of wedge to improve the control of the barrel explained that when we use this wedge, the mechanical efficiency increase because the vertical force is better and is more perpendicular than the previous situation. John needs to ask about that because there are some studies talking about if the wedge doesn't help the cyclist to increase that power. John? I think John has some problem of connection, so I will go on.
Yeah, this is one of the last studies. Yeah,
Yes,
can you hear me?
yes, yes.
Yeah? Yeah,
Yeah.
okay, yeah. There are several studies that are investing. Hello?
Yes. John?
Yeah, Javi. I'm on. Can you hear me well?
Yes, yes, I can hear you.
Okay, so there are several studies that they speak about the phenomenon of the wedging, but this only one is talking about the mechanical efficiency and the influence of the wedging on that. And it seems that the correct compensation of down increases the mechanical efficiency. It was another word talking just about the anaerobic metabolism and performance, and this one that is quite new is speaking about the aerobic metabolism. So I think that is a quite important risk that sometimes happens.
Okay. About what is the importance of a bike fitting or a biomechanical screening, there are two important studies of Batterman in 2004 and Coyle in 1995. Both of them explain that thanks to a bike fitting, increase in the mechanical efficiency in the study of Batterman explained from 2.7%, and the study of Coyle explained that 1 or 2% in gross efficiency. So obviously at higher level, a biomechanical screening or a bike fitting is important in order to increase that situation. Now John is going to explain the classic study of HAB, the transit HAB, about the muscle activation, the model of muscle activation, and the different factors that can affect it.
Yeah. obviously, if we change some of the models as we are pedaling from different technical point of views, we can arrive to different models, and we can arrive also to different onset and offset.
I think that John has some problem of connection.
Of the muscles that they are using. This is the main important conclusion. Yeah, can you hear me now?
Yes.
Hello?
Sometimes we lost the signal. John?
Yeah. Yeah, yeah. Can you hear me now?
Yes, yes.
Yeah. I just explaining about the different way of pedaling makes different patterns of uses of the muscles. There are main figures that they do exactly the same pattern, but it depending on each one's configuration and each one motor pattern, the motor of those muscles are different. So this is important. It's related with the next slide. Please, if you can follow on to the next one. Yeah, when Sanderson somehow explained that several factors, for example, the fatigue, change the way of using the muscles, and because of those changes in the muscles, became some change in the mechanical efficiency, because you are not able for put it on maybe the strength in the correct right position because you are fatigued. So it's quite clear. For example, today at the tour, at the end of the stage, we have seen very fatigued and not very powerful Chris Froome making a lot of ankling, as during the stage has not been very visible to be ankling. At the end was just the only possibility of making the maximum power sustained. So has been very visible, and we'll try to recover the video because I think it's very clear the case that when you are fatigued, you are going to change the motor pattern of your muscle, that is going to change also the mechanical efficiency of pedaling.
This is another study, in this case by Bini and Diefenthaler, and explain how that this mechanical efficiency doesn't decrease with the fatigue. Some people can explain that when the cyclist is with more fatigue, that mechanical efficiency decrease, but as John has explained, during a stage, for example, at the end, the cyclist use the more muscles as possible to keep on with this mechanical efficiency. But obviously the metabolic cost, and you can see in this image below. Now John is going to explain this study of Kitawaki in 2004, but in this study is very interesting, the conclusions about the weights and the cadence, and now John is going to explain us.
Yeah, on this study is somehow explained that the weight of the leg is very closely related with the mechanical efficiency. On this way, the more mass it's on the leg is probably going to be worse from the point of view of mechanical efficiency. So lighter legs are going to pedal in better than the more stronger or at least more bigger or weighted ones. On this case also, it's demonstrated that the mechanical efficiency
We lost the signal again.
with intensity. It's something that is repeated during the. So we are quite sure in the research, and there's a lot of consensus when we talk about the pedaling efficiency that is increasing with the intensity, and it's also demonstrated on this study of Kitawaki.
About the use of insoles, this study of Colin Meyers explained that insoles improves the muscular implications, but doesn't improve the performance in short term. It could be interesting to study how that improvement in muscular implication will or might affect the performance in a future. but at the moment, the evidence explains that the use of insoles doesn't increase the performance at the moment. And now John is going to explain this study about cadence oscillation. He has been working with accelerometers in the cranks, studying the percentage of variation of the speed while pedaling, and I think that he can explain us a lot of conclusion about this and have a relationship with this study of Kitawaki.
That we cannot make distinction between a different variation of the speeds on the crank, as we expect it to be very related with the mechanical efficiency from the point of view of making a good pedaling and a bad pedaling, and this is not true. It's much more related with the ability of maintaining and sustaining one concrete cadence for one rider. So when the rider is out of this, to be a very big variation of the pedaling speed from the top, that's downstroke, that is normally those points are the more fastest one in general. What happens on those cases that out of your cadence you are not able for maintaining this kind of inertial pedaling, you are going to lose speed pedaling, and it is closely related with the decrease of the mechanical efficiency. So we can just measuring the movement of the leg from the point of view of the maximum and minimum speed to know exactly what is going to happen to the point from the point of view of the mechanical efficiency. Because when the pedaling is stopped in the upper part of the stroke, when the GPA is maximum, the data is going to be worse and worse. So the reason that we are not able for maintaining the speed is basically because in the upstroke we are not able for pulling up the leg at the same that the pedal is coming. So I think that this is going to be a very important factor in the future to try to give a good feedback to the riders to try to maintain their own pedaling and their own cadence, because out of this normally the mechanical efficiency is not good, it's not going to be better than the self-selected one.
To sum up the evidence for how we can optimize the metabolic efficiency, we have seen in a lot of study, training at high intensity, the known HIIT, and self-selected cadence, or slightly lower than usual, 18-19. And about ankling, it's important to not decrease the metabolic efficiency, as we have said in the example of WKO4 and the study of CAP. And for optimizing the mechanical efficiency, it's important to know the sport level. We are pro or amateurs, our level of training, the position of the body and the inclination, and rotate of the saddle, the body center, and the stabilization of the foot, of course, with wedge. It's important the feedback of our pedaling. We said in the study of Bini how lead feedback, and in the study of Thurwell too, with lead feedback, the pedaling mechanical efficiency increase, and obviously symmetrize or the movement through education of the gesture. And of course, optimize the ascending of the phase of pedaling. That doesn't mean not to pull the pedal, but it's important to prolong a little the pushing phase. Now we have done a little experiment with WKO4 and with cyclosphere analysis of the pioneer page. We told one cyclist to pedal at the same cadence with the same resistance in the trainer, but with different pedaling techniques. And now we are going to see the different data that the WKO4 show us. You can see that the cadence that we told the cyclist to pedal was 82 RPM, and the first one we told the cyclist to pull the pedal. So we said that you have to make the emphasis in this part of the pedaling, and you can see how the vectors are pulling all the time or are in the direction of the pedaling. And you can see what happens. GPA decrease, obviously, but at the same time, the GPR was lower as we are going in comparison with other pedaling technique like cycling or pushing that we are going to see later. You can see that the pedaling efficiency was 47 for this pedaling technique. What happened when we told the cyclist to pedal in circling? The first thing is that the production of power increased so much. You have seen that in the other case, the cyclist produced 190 watts, and now he produced 100 watts more. The pedaling efficiency increased because you can see here that there is low GPA, but at the same time you have high GPR in comparison with the pulling. You see here that, no, pardon, this one. In pulling, the GPR was so low, but in the circling, the GPR increased and low the GPA. What was the problem with this pedaling technique? The cyclist wasn't able to maintain it more than 5 minutes. He was in total fatigue because his FTP is in 220, and we told him to pedal with this kind of technique, and he goes to over 300 watts. So you can see here the vectors. They are tangential in all the cycling and or the pedaling circle, but it was difficult to maintain for him. So the much power you produce, obviously, the most metabolic cost. The last one, we told him to make inertia or pushing pedaling, and we can see that this pedaling style produce good values of GPR and normal values of GPA. So we can sum up that this pedaling technique, it could be the best for doing submaximal efforts, or when we are, for example, working in aerobic or tempo street sport, or why not at FTP. And where we want to go further, the circling pedaling technique could be the best. Anything to add, John, about this one?
No, I think that on those guidelines, it's more or less explain it, or at least resume it, the evidence actually to try to use the better way of pedaling. As you say, below the FTP and above 60% training, they are useful for developing a better mechanical and metabolic efficiency. But on those cases, we are going to try to sustain very hard pushing. So we try to concentrate in the downstroke, trying not to avoid to stop, but always taking a look to not losing on speed when we are pedaling. When we change the technique, for example, for trying to pull out from the pedals or make some circles just for doing very high level efforts that they are supramaximals sometimes, and they are not very sustainable because probably they are going to increase the metabolic efficiency, so they
Seems that John has problem with the connection. I was explaining the same that I have said when John, we have lost the signal.
Yeah, I think that sometimes it's good at my connection. Yeah.
Yes.
Yeah. Can you hear me now?
Yes.
So yeah, I was explaining about the use of the pedaling of cyclings in the supramaximal efforts and the pedaling from a partial point of view in the intensity levels below the FTP.
Things that we have not conclusive scientific evidence on the improvement of the gesture, high cadence training, low intensity training, positioning of the knee on the pedal axis, symmetry, core, position of the cleats, connecting current length, and relationship between mechanical and metabolic efficiency. There are the topics that are with no scientific evidence at the moment, we have seen in this webinar. What is the take-home idea? That enhance the mechanical efficiency doesn't mean that that always improves the metabolic efficiency. So, John?
Yeah, I think that's the most important thing, because nowadays we are able for measuring the mechanical efficiency in a very easy way with the dual-sided power meters, and there are several also devices that give us this data in instant way, but several times we do several things, both mechanical and biomechanical adaptations, and we increase the mechanical efficiency. But this doesn't mean that we are going to increase at the same time the metabolic efficiency. So there are just a few things that we can do to increase the mechanical efficiency and the metabolic efficiency at both times, because increase the metabolic efficiency is quite easy when you got feedback, but several times, as I said, doesn't mean that it's going to be a big or better performance, because the mechanical efficiency is going to be higher too. So it means that we are going to have more power, where we are going to get more fatigued too. So several times, those are the resistance and the endurance point of view of the cycling.
About new perspective with the use of WKO4, now they are developing some charts that Garmin Cycling Dynamics, and I know they are working with other trend marks of power meters, and these charts are very interesting because we can make a deep analysis about the pedaling technique of our cycle. For example, in this one of Garmin, we can see, for example, in which moments we are making the power pass, the angle, the timing. So they will give us much more deeper information than GPR and GPA. In the future, we could give more feedback to our cyclists thanks to WKO4 and this type of charts linked to different types of dual power meters. So thank you very much to Training Peaks for the invitation. It's an honor for us being here, and we will let you do our emails. If you have any doubt or any question, you can send us. Okay.